In this class, we'll study knowledge-based systems. We'll first take a look at what it is and study a specific type of logic system called propositional logic that we can use to build knowledge-based systems. On the first day of the class, we studied that there could be many different ways to define AI and that these definitions can be grouped into 4 schools of thought. When it comes to knowledge-based systems, we're in the domain of thinking rationally, which means we're going to focus on how the agent thinks, and also we're going to make agents that think rationally rather than humanly. When we work on different tasks, we make use of knowledge that's relevant for the task. We can call this background knowledge. And the more background knowledge you have about a problem, the easier it is to solve it. This is true for pretty much any tasks, but especially true for understanding language. Suppose we are trying to figure out the meaning of the word flies in these 2 sentences. We know that in the first case, time flies like an arrow. Flies is used as a verb, whereas in fruit flies like a banana, it's used as a noun. If you look at the grammatic structure of these 2 sentences, they're very similar, but we were able to distinguish the 2 because we know that there are such things as fruit flies, whereas there's no such thing as time flies. Another example would be coreference resolution. So how do you know which word the pronoun it is referring to? Okay, so in the first case, we have John saw the diamond through the window and coveted it. So it refers to diamond because, window is not worth as much and you don't really covet window. And in the second sentence, we have John threw the brick through the window and broke it. And this time it refers to window because we know that bricks can break windows, but not vice versa. So in both of these examples, we made use of our knowledge about the world to decide which noun the given pronoun refers to. Knowledge-based systems consist of 2 main components, knowledge and inference mechanism. Knowledge is a set of facts or pieces of knowledge that you know, and inference mechanism tells you how you can expand on that to build new knowledge. In fact, this is very similar to how human brain works. Suppose you know that animals have to eat to survive, and that cat is an animal, then you can infer that cats have to eat to survive. And when it comes to representing knowledge, we have to pick a logical language which comes with inference mechanisms. We'll first look at propositional logic, which is the simplest logic system. To see how knowledge-based agents behave, we're going to take a look at an example called Wumpus World. In this game,
the goal is to find the gold
while avoiding dangers like a wumpus or pits. The agent doesn't know much about the world, but knows certain things. Like when you're next to a pit, you can feel the breeze. When you're next to wumpus, you can smell the stench. When you're next to the gold, you can see the glitter. Again, the agent starts off with very limited knowledge about this world, but by making inferences and experiencing the world, you learn more and more about the world and eventually find gold while avoiding the dangers. So let's take a look at an example. So suppose the agent is at the bottom left location. Given that the agent does not feel any breeze, smell anything, or see any glitter, the agent knows that it's fine to go up or go to the right. And suppose we decide to go up and we feel the breeze. So what does that mean? Well, that means there could be a pit above or to the right. We don't know which of the 2 is a pit, and in fact, they could both be pits. And since we're not sure, we want to explore the one remaining safe ground, which is here. And suppose we go there and we smell stench. What does that mean? If we smell stench, it could either be wumpus here or wumpus here. But then we didn't have stench here, so this cannot be wumpus. And we don't have a breeze here, which means this cannot be pit. And that means this actually has to be the pit, and this has to be the Wumpus. And based on this observation, we know that this location is safe to go. Suppose we move there and we don't feel anything, which means these two locations are also safe. And suppose we visit the location on the right first, and we feel the breeze and also the stench. Again, what does that mean? Well, we could have a pit to the above or to the right. And if we assume that there's only one Wumpus, then we can kind of forget about the stench, because we already know that the Wumpus is down here. To the right and to above, we might have pits, so we're not really sure which of those locations will be safe. So we're going to go back and go up to what we know is safe for sure. And suppose when we got there, we feel the breeze and then we see glitter. Okay, if we feel the breeze, that means any of these could be pits. And then if we see the glitter, I guess that cell could contain gold. When it comes to gold, the only possibility is the gold being at this cell. So gold has to be there. And then if we assume that gold cannot be in a pit, then we know that this cell is not a pit. So we successfully found the gold while avoiding the Wumpus and the pits. We started off with very little knowledge about this world, and using the facts and inference mechanism we have, we were able to expand our knowledge and search through this space in a safe manner. Another example is autonomous car. Say the autonomous car can observe things like, is there a person in the front? Is there a policeman? Is the road slippery? And so on and so forth. And then say the possible actions are brake, accelerate, turn left, and so on. And this is our knowledge that we start off with, which is if there's a person in front, you have to brake. If the light is yellow and there's a policeman and the road is not slippery, then brake. And then, a few other knowledge that we have. Given this setup, if you know that there's a police car and the light is yellow and it's snowy, would the car brake? You may want to pause the video before you move on. There are different ways to go about it, but there are only 3 cases in which the car brakes. In the first case, we have to know if there's a person in front, which we don't know, so we can't use that rule. In the second case, we have to know that the light is yellow, which we do know, and we have to know if there's a policeman, and we have to know if the road is not slippery. We know that there's a policeman because we know there's a police car, and if there is a police car, there is a policeman. Okay, so the question is the road not slippery? Well, it says if it snows, which we know is the case, then road is slippery. So the statement road is not slippery is not true. So we cannot make use of that. And then lastly, to brake, we have to know if the light is red and it's not red, so it's not going to brake. So the answer is no. The car does not brake. The same scenario can be expressed using propositional logic rather than natural language. So instead of having, English sentences, we have things like person in front of car implies brake, yellow light and policeman and not slippery implies brake, and so on and so forth. If you're not familiar with propositional logic, that's fine. We're going to spend more time on it later today. So we can still ask the same question. If police car is true, yellow light is true, snow is true, will it brake? Obviously, you get the same answer. And we can go even more extreme and use variables that are not really meaningful, but it still represents the same case. And we can still do the same inference. Which system of logic we use determines how knowledge is stored and also what kind of inferences are possible. When it comes to individual pieces of knowledge stored as sentence, there are 2 aspects of a sentence. One is the syntax, what is the grammatic structure, and then semantics is what's the meaning of that. For example, in math, x plus y equals 4 is a syntactically valid sentence, whereas xy plus equals 4 is not. And then the semantics is just a truth value. The sentence x plus y equals 4 is true if x equals 2 and y equals 2. And we have this concept of model, And you can think of a model or a world as an instantiation of all the variables. So you're giving a value to every single variable you define. And then M of alpha refers to the set of all models or all worlds that satisfy the sentence alpha. Suppose alpha is x plus y is 4, then M of alpha would be basically the set of all instantiations of x and y such that x plus y is 4. So it could be like x is 0, y is 4. That's one model or one world. But you could also have a different model where x is 1, y is 3, and so on and so forth. And we say alpha is valid if it's true in every model, and alpha is satisfiable if it's true in at least one model. We define the concept of entailment as follows. Alpha entails beta if and only if M of alpha is a subset of M of beta. So this means entails. And graphically, this means that suppose we have many different models. Say this is M of alpha. So these are the models in which alpha is valid or alpha is true. Then what we're saying is alpha entails beta if M of alpha is a subset of M of beta. Basically, if we are in a world in which alpha is true, then beta is true, but not necessarily the other way around. Let's consider a very simple 1+ world consisting of 5 cells. And let's suppose that we know that there's nothing in cell 1,1 and breeze in cell 2,1. And we can have pits in cells 1,2, 2,2, and 3,1. So these are all possible worlds. For each of these cells, 1, 2, 2, 2, and 3, 1, you could either have a pit or not. So we have a total of 8 worlds. And the solid line represents M of KB. So the models in which KB is true. The middle one is not correct because if there's breeze in 2,1, then there has to be a pit here or here, and neither is the case. And if there's nothing in 1,1, you cannot have a pit at 1,2. So none of these work. So the solid line represents MKB. And the dotted line represents M of alpha 1, where alpha 1 is no pit in 1, 2. So these are all the worlds in which there's no pit in 1, 2. In this case, which of the following is true? Again, you may want to stop the video. Well, MKB is a subset of M alpha 1, so B must be true. In other words, if you're in a world in which the knowledge base is true, then alpha 1 is also true, but not vice versa. So let's consider the same setup with the different alpha, alpha 2. And alpha 2 says there's no pit in 1, 2. So there's no pit here. In this situation, which of the following are true? Simply put, MKB is not a subset of M alpha 2, and nor is M alpha 2 a subset of MKB. Okay, now let's look into a specific type of logic called propositional logic. In propositional logic, you have 2 main components, which are symbols and connectives. The symbols could be just letters, or it could be more meaningful, like police car. Is there a police car nearby? Or is the light yellow? And then the connectives are not, and, or, and implication. Going one way or both ways. Using these components, you can write sentences. A sentence is the smallest unit that can hold knowledge. In the simplest case, you have atomic sentences like true. So true is a sentence, false is a sentence, and then you could just have a symbol that's a sentence. And then you can have more complex sentences by using connectives and these atomic sentences. Here's a truth table. In a truth table, you have a row for every combination of truth values for the symbols. Since we have 2 symbols in this case, you have 4 rows. And you can think of these as the models or the worlds that we're going to consider. And for each of the world, we're going to consider the truth value of the sentences that we're interested in. For example, if you consider the sentence not P, in the world in which P is false, the truth value of the sentence is true, and then false otherwise. And the NORs are all straightforward. If you consider the sentence P and Q, it's true only in the world in which P and Q are both true. And then it's false in all other worlds. And P or Q, that sentence is true in any world in which either P or Q or both are true. And then false otherwise. How about P implies Q? What does that mean? Well, this means whenever P is true, Q has to be true. So let's first consider the worlds in which P is true. So these two. In order for the sentence P implies Q to be true, Q has to be true. So if they're both true, P implies Q is true. But if P is true but Q is false, then P implies Q is not true. Now let's consider the worlds in which P is false. What value does Q has to have in order for P implies Q to be true? It turns out that the value of Q doesn't matter. In either case, P implies Q is true. This may sound a bit unintuitive, but if you think about what P implies Q means, it would make sense, right? So P implies Q says, if P is true, then Q has to be true. But if P is not true to begin with, then we know nothing about Q. Okay, lastly, the double implication. So this means that P implies Q and Q implies P. Let's first consider Q implies P. So that means, again, if Q is true, P has to be true. So if Q is true, P has to be true. If Q is true but P is false, then Q implies P is false. When Q is false, P could be anything. When P implies Q is true and Q implies P is true, then the double implication is true. So it's going to be T, F, F, T. Or you can also think of the double implication as equivalence. So when you have P if and only if Q, then you're just asking, are they equal? In the first world, they're equal. In the last world, they're equal, but in the middle two, they're not. So that's how you get T, F, F, T. So let's consider a question. Is P implies Q equivalent to not P or Q? Again, you can pause the video for a bit until you finish this. Well, we already know the truth values for P implies Q. So I guess it will be helpful if we knew the truth values for not P or Q. So we're looking at the not P column and then the Q column. So if either of those are true, then not P or Q is true. First world, not P is true, so not P or Q is true. Second world, they're both true, true. Third, neither are true, so it's false. Fourth, Q is true. And it turns out that P implies Q and not P or Q have the same truth value in all the worlds, which means they're equivalent. So they're interchangeable. There are some interesting facts about propositional logic which don't seem very intuitive at first. The first thing is inference does not mean causality. The sentence 5 is odd implies Seoul is the capital of South Korea is true because P implies Q is true when P is true and Q is true. So this sentence is a true sentence, but it doesn't mean that 5 being odd has a causal relationship with Seoul being the capital of South Korea. And the second thing is that false implies everything. We know that P implies Q is true when P is false, regardless of Q. Since this is false, anything could come here and the whole sentence will still be true. Again, knowledge-based systems consist of two components, the knowledge and inference mechanism. And we'll see how they look when we are using propositional logic for our system. So let's first look at knowledge base using propositional logic. Let's consider the 1 plus world example again. First, we have to decide what the symbols are going to be. We can have symbols like whether there's a pit, whether there's a breeze, whether there's a wumpus, and so on and so forth. So let's say Pij is true if there's a pit at position ij. So Pij is a symbol that's either true or false. And similarly, we could do Bij, which is true if there's a breeze at the location and false otherwise. And then we can also do that for wumpus, glitter, gold, stench, and so on. So these are our symbols. Using these symbols, we can encode knowledge as follows. The sentence, there is no pit in 1-1 would be equivalent to not P11. And if we want to say that the cells next to pit is breezy, we can say something like B11 if and only if P12 or P21. And we actually have to do that for every cell in the map, which is kind of cumbersome, but still possible. So this is the knowledge we start with. And as you play this game and get more information about this world, then you add more knowledge to your knowledge base. For instance, if you felt no breeze in 1-1, then you add not B11. And then, if you felt breeze in 2-1, then you add B21. So this knowledge base gets bigger and bigger as you experience the world. And this is an example we saw before. You start off with rules like person in front of the car implies brake, and so on and so forth. So these are the things even before you know anything about the world. And then once you experience the world, you see things like, oh, there's yellow light, there's no red light, there's no snow, dry, police car, and so on and so forth. So that was our knowledge base. And then let's talk about inference. Given our knowledge base, we want to be able to drive new conclusion Q, where Q is just a sentence that would be true as long as every sentence in knowledge base is true. And the same thing can be thought of as showing that the knowledge base entails Q. So what does it mean for the knowledge base to entail Q? That means in any world in which all the sentences in the knowledge base are true, Q is also true. And this is equivalent to saying there's no world in which every sentence in the knowledge base is true, yet Q is not true. Let's look at how we actually prove this. We're going to look at model checking and logical inference. And model checking is quite straightforward. Again, the goal is to show that the knowledge base entails Q, which can also be done by showing that there's no world in which knowledge base and not Q is true. And in model checking, this is done by building a truth table that enumerates all possible worlds. So let's suppose we have two symbols, P and Q, each representing the street is wet and it's raining. And suppose we want to derive a new piece of information saying not P and Q implies P, the whole thing implies not Q. We're going to show that the negation of this sentence is not satisfiable. How is the second sentence the negation of the first sentence? Well, we're going to make use of two facts. One, A implies B is the same as not A or B. And second, the negation of A or B, so not A or B, the same as not A and not B. When we use 1, so this is A and this is B, then we get not P and Q implies P, or not Q. Suppose we take the negation of that, negation of this whole thing. And there, if we use the second rule, this would be A and this would be B. We just have the negation of A and negation of B. And negation of A is just double negation, so we get rid of the outer negation. So we're left with not P and Q implies P. Okay. And we have not B, which is just Q. And that's how we get this thing. So going back to what we were doing, in model checking, to show that the second sentence is not satisfiable, we just enumerate all worlds. So basically all combinations of trues and falses for P and Q, and make sure that the sentence is always false. So we would hope that these are all false. And you might want to pause the video at this point and just make sure you can fill this out yourself. So not P is pretty straightforward. It's false, false, true, true. Q implies P. So whenever Q is true, P has to be true. If Q is false, P can be anything. If Q is true, P has to be true. And then if Q is false, P could be anything. And then not P and Q implies P, then whichever row has T for both, which is just the last one. And then the last column, which is actually what we're trying to show that is not satisfiable. It has to be the case where the second to last column and Q both have to be true, but there's no such world. So we have shown that the negation of the sentence that we're trying to show is not satisfiable. So this is how model checking works. The downside is that model checking doesn't scale because you have to check all worlds which involve enumerating the truth values for all the symbols. And typically in real world applications, you have a lot of symbols. So next class, we'll look at something called logical inference, which scales much better than model checking.